Okay, good day, class. Today we'll be discussing sample problem for the compressibility of the soil. So last meeting, we discussed the concept behind the compressibility or the consolidation of soil of a given soil. Okay, so for this topic, okay, so for example one, a 3-meter thick clay layer is beneath a 7-meter sand layer with the groundwater table located 2 meters below the ground surface. So if a uniformly distributed load, or denoted as sigma delta sigma prime, yeah, that is 75 kilonewton per square meter, is applied at the ground surface, so what will be the settlement of the clay caused by the primary consolidation? So again, we are given that our sigma prime C, or the pre-consolidation pressure for the clay, is 125 kilonewton per square meter, and the swell index is 1/5 of the compression index. Okay, so given that the saturated unit weight of sand is 18 kilonewton per cubic meter and the dry unit weight of sand is 16 kilonewton per cubic meter, and for the clay, the saturated unit weight of clay is 19 kilonewton per cubic meter, the in situ void ratio, that is 0.8, and the liquid limit, that is 40. Okay, so writing our given datas. Okay, so according to the problem, we have a 7-meter thick of sand layer at the top of the clay layer of a 3-meter thick clay layer. So this is our soil profile. Okay, and further we have 2 meters of groundwater table below the ground surface. So this is the location of our groundwater table. Okay, and writing our unit weight. So we have a dry unit weight of 2 meters at sand layer, that is 16 kilonewton per cubic meter. Saturated unit weight of 18, saturated unit weight of clay, that is 19, and the in situ void ratio of 0.8, and a liquid limit of 40. Okay. Then also we have an induced pressure at the top, or the delta sigma prime, or the load at the top of our at the ground surface of our soil profile. Okay, so we are again considering the mid portion, or the mid height of the clay layer. So we are getting a soil sample at the mid height of the clay layer. So during our discussion last meeting, the farthest distance that soil is travel in the is at the middle of the clay. So we are considering the mid height of the clay. Okay, so for our problem, we need to find the consolidation of our clay layer. Okay, so we need to solve first the effective stress at the mid portion of the clay, so this location. Okay, if you remember the formula for the effective stress, that is the total stress that is equals to the effective stress plus the pore water pressure. So in order to get the effective stress, you need to find the total stress minus the pore water pressure. Okay, so therefore, the effective stress at the the mid height of the clay is gamma dry of the sand multiplied by 2 meters plus, so since our sand is saturated, so we need to subtract that to our unit weight of water. So that is gamma saturated of sand minus the unit weight of water times 5 meters plus the saturated unit weight of clay minus unit weight of water times 1.5. 1.5 is the mid height of the clay. Okay, so inputting the values, we have 16 times 2 plus 18 minus 9.81 kilonewton per cubic meters for the unit weight of water multiplied by 5 plus 19 minus 9.81 times 1.5. Again, then again, we have an effective stress of 86.74 kilonewton per square meter. Okay, then solving for the checking if our effective stress is less than or greater than the pre-consolidation pressure. So we need to find first if that is a normally consolidated clay layer or a over-consolidated clay layer. Okay, so since our effective stress is less than the pre-consolidation pressure of 125 kilonewton per square meter, therefore our soil is over-consolidated. So for the case of over-consolidated, they have two conditions. Condition one is if the sum, okay, we need to check the two cases. So if the sum of the effective stress and the induced pressure compared to the pre-consolidation pressure. Okay, so we need to solve for that. Okay, so for the effective stress, we have 86.74 plus the induced pressure at the top or at the ground surface is 75 kilonewton per square meter. Okay, and the pre-consolidation pressure of 125. So obviously, that is the sum of these two values is greater than 125. Therefore, we are checking case 2, okay, or condition 2. Okay, so for condition 2, the given formula for the primary settlement of over-consolidated clay layer that is under case 2 is given by this formula. That is CS, swell index, times the height of the clay layer over, or the thickness of the clay layer, plus 1 plus in situ void ratio multiplied by the logarithm of pre-consolidation pressure over the overburden pressure or the effective stress, plus the compression index multiplied by H over 1 plus E sub 0 log of overburden pressure or the effective stress plus the induced pressure at the top over the pre-consolidation pressure. So let's see if we have all the values. So we have this one, we have H, we have E sub 0, we have the pre-consolidation pressure, overburden pressure, we also have the induced pressure, okay, and H is sub 0. So what we have left is the swell index and the compression index. So according to the problem, we have our swell index of 1/5 of the compression index. So therefore, we need to first find what is the value of the compression index. So recall the value of the formula for getting the value of compression index. So compression index is since our problem is given by LL, that is liquid limit of 40. So we need to use the Skempton formula or the Skempton equation. So under the Skempton equation, we are considering if our soil of our soil sample is undisturbed or a disturbed soil sample. So in our case, we are considering undisturbed soil, or this one. Okay, so we are assuming that our soil is undisturbed. So this is our default assumption. Okay, so for the swell, the compression index that is given by the equation of Skempton formula, that is 0.009 LL minus 10. So that is 0.27. So we have a compression index of 0.27. Therefore, our swell index is 1/5 of that CC. That is 0.054. So now we are able to be able to solve for the primary settlement. Okay, so plug in all the values. Okay, so we have this equation. So SP, or the primary settlement, is equivalent to 0.06464 meter or 64.64 millimeters. So take note that our H, the value of H, is in meters. Okay, that is in meters. So that is why our first value of the value that we get is 0.06464. That is in terms of a unit of meter. Okay, so multiply that by 1,000, you get a 64.64 millimeter primary settlement. Okay, so that is our answer for example problem 1. Okay, so you just need to find the if pre-consolidation settlement. So you need to check that if the given problem is under normally consolidated or over consolidated. So under over consolidated, we have two conditions. So we need to check if which case you need to consider. Okay. Again, for sample problem 2 or example problem 2, the soil profile shown at the site is given in the figure. Okay, this one. So the moist and saturated unit weight of the sand is 17 kilonewton cubic meter and 20 kilonewton per cubic meter respectively. So a soil specimen was taken from the middle of the clay layer and subjected to a consolidation test, and the following properties are reported. So that the natural moisture content, that is 22.5%. We have a specific gravity of the soil, that is 2.72, a pre-consolidation pressure of 110 kPa or kilonewton per square meter, a compression index of 0.52, and a swell index of 0.06. So according to the problem, what is the problem is it normally consolidated or over consolidated soil, or if over consolidated, what is the over consolidation ratio? And number 2, if a 2-meter high compacted field with a unit weight of 20 kilonewton per cubic meter is placed at the top of the ground, then what would be the final consolidation settlement? Okay. So first thing to do is to write all the given data. So we have moisture content of 22.5%, SG or the specific gravity is 2.72, a pre-consolidation pressure of 110, compression index of 0.52, and the swell index of 0.06. Okay, then we have a soil profile. Okay, so according to the problem, we have a 2-meter sand, dry sand at the top, groundwater table 2 meters below the ground surface, a 3-meter thick na sand that is saturated, and a 3-meter thick of clay that is saturated. Okay, so writing all the unit weight, we have the dry unit weight of 17, a saturated unit weight of sand that is 20. So we need to find the saturated unit weight of clay. So we don't have a data for the saturated unit weight of the clay. So in order for us to solve for the problem, we need first to determine the saturated unit weight of a clay layer. Okay, so given all the data, this one, so how to solve for the saturated unit weight of the clay? Okay, so for the solution, if normally consolidated or over consolidated, so you just need to check if the pre-consolidation pressure versus the effective overburden pressure or the effective stress at the present. Okay, so first thing to do is find the saturated unit weight of the clay. So how to do that? So you need to recall the formula for the unit weight of a soil. Okay, so given the specific gravity, a saturation, and the void ratio. Okay, so where S is equals to 1, that is when saturated, and S equals to 0 when the soil is dry. So use this formula. Okay, use this formula. So again, a relationship of the saturation multiplied by the void ratio, that is equals to the moisture content multiplied by the specific gravity. So from that relationship, okay, from your geotechnical engineering 1, from this relationship, we can get the void ratio of our saturated clay. Okay, so to solve for the void ratio of the saturated clay, just put S equals to 1 when saturated, then unknown value E, a unit weight of 0.225 in decimal, and a specific gravity of 2.72. So therefore, we get the void ratio of 0.612. Okay, so now we can solve for the saturated unit weight of our clay. So just plug in the values. So GS what is 2.72 plus 1.0 when S is equals to 1 when saturated. So that is 100% under water. So that is S equals to 1. Okay, void ratio of 0.612 over 1 plus E multiplied by the unit weight of water. So we are using 9.81 kilonewton per cubic meter na unit. Okay, so that is kilonewton per cubic meter. So therefore, we have a saturated unit weight of clay that is 20.3 kilonewton per cubic meter. Okay. Now, solve for the present overburden pressure or the effective stress. Okay, so we are getting the sample at the mid height of the clay layer. So at this level, so we are always considering at the mid level of the clay. So since that is the farthest distance that soil molecules will travel, okay, that is this one. So solving for the overburden pressure, okay. So present overburden pressure, so unit weight of dry sand times 2.0 thick plus the difference of the saturated unit weight of sand minus the pore water pressure multiplied by the thickness of 3 meters and the difference of saturated unit weight of clay minus the pore water pressure, okay, multiplied by 1.5. Again, this is you should write comma right here and this one. Ayan. So in order to solve for the present overburden pressure or the effective stress, okay, so plug in all the values. We have the overburden stress of 80.3 kilonewton per square meter. So that is our effective stress. So now comparing our effective stress to the pre-consolidation pressure of 110, we can say that the effective stress is less than the pre-consolidation pressure. So if less than the condition, if the pre-consolidation pressure is greater than the overburden, or the overburden that is less than to the pre-consolidation pressure, so that is over consolidated. Okay, over consolidated yung if the pass or the pre-consolidation pressure is greater than the present overburden stress or the present effective stress. So answering the problem, if the soil is normally consolidated or over consolidated, our soil is over consolidated. Then solving for the over consolidation ratio. So for the formula of the over consolidation ratio, that is the ratio of the pre-consolidation pressure over the overburden stress or the effective stress. So 110 divided by 80.3, we have OCR or over consolidation ratio of 1.37. So therefore, this is our answer for problem A. Okay, so next problem. If as a 2-meter high compacted fill is added to the ground surface with a unit weight, okay, ang unit weight po niya is 20 kilonewton per cubic meter. That is a 2-meter fill. So imagine you need to embank or fill the ground surface of a 2-meter thick of soil which has a unit weight of 20 kilonewton per cubic meter. So in order for us to solve for the delta sigma prime or the induced pressure at the top, so just simply multiply the height and the unit weight. So that is 2.0 multiplied by 20. We have the induced pressure at the ground surface of 40 kilonewton per cubic per square meter, or 40 kPa. Okay. So from the previous, just rewrite the over consolidation of 80.3 and the pre-consolidation pressure of 110. So we need to check if our case is condition 1 or case 1 or case 2, since our given sample is also an over-consolidated clay. So under a over-consolidated clay, we have 2 cases. So just check the sum of the overburden pressure or the effective stress plus the induced pressure and the pre-consolidation pressure. Okay, just add that, this one. You get 80.3 plus 40. Okay, compare that to the pre-consolidation pressure of 110. So 80.3 plus 40, that is 120.3. That is greater than the pre-consolidation ratio. Therefore, that is case 2 or condition 2. So the formula for the pre-consolidation settlement, okay? So primary consolidation settlement, this one, that is given by this formula. So yung mahaba ulit. So let us check if we all have the values in this formula. So we have H, we have E sub 0, okay? So pre-consolidation pressure, overburden stress, H, E sub 0, and effective stress, induced pressure. Okay, so we have all the followings. So given that are given from the problem that the compression index of 0.52 and as well index of 0.06, we get the primary settlement of this formula. So CS, that is 0.06. The thickness of the clay, that is 3 meters over 1 plus 0.612. The in situ void ratio multiplied by the logarithm of the pre-consolidation pressure over the overburden stress or the effective stress, that is 80.3. A plus CC, that is compression index multiplied by the thickness of the clay over 1 plus E sub 0, then multiplied by the logarithm of the sum of the overburden stress and the pre-consolidation pressure divided by the overburden stress and induced pressure divided by the pre-consolidation pressure. So that is the value of SP is 52.9 millimeters. So our unit is in millimeters since our value of H is in millimeters. This one is in millimeters. So we have a primary settlement of 52.9 millimeters. Okay. Now, our next problem for a normally consolidated soil with 3-meter thick of clay layer in the field is subjected to an induced stress of 50 kilonewton per square meter. Then additional data are given. The in situ void ratio of 0.8, a compression index of 0.28, an average effective pressure on the clay layer or the effective pressure at the mid portion or at the mid height of the clay layer, that is 130 kilonewton per square meter, and a secondary compression index of 0.02. The problem is, what is the total consolidation settlement of the clay layer 5 years after the completion of primary consolidation settlement? Then it is noted that it was found out that the time of completion of the primary settlement takes up about 1.5 years. Okay. So given all the datas, okay, this one. So T sub 1 or your time to the time in order to complete the pre-consolidation settlement, that is 1.5 years. Okay. So note that it says that the soil is normally consolidated. Thus, our formula for the primary settlement is given by this equation. So for normally consolidated clay layer or clay soil. So for normally consolidated clay soil, we have this formula. Okay, just plug in all the values. Okay, and for the secondary consolidation settlement, we also have this formula. So we have the swell index C alpha, the HP or the height after the complete height of or the thickness of the clay after the complete primary settlement, and the void ratio at the final of pre-consolidate of primary settlement. Okay, so we need to find all the values. So solving for E sub P, okay, so kasi nga, okay, this one. So for this one, we have C sub C, we have height of the clay, initial height of the clay, we have in situ void ratio, we have the effective stress and the induced pressure. Okay, then we have C alpha or the swell index. We have the time T2. So you want to find the total settlement at time 2, at time 5 years, and the T1, that is the time for complete primary settlement. Okay, so what we have left is HP and EP. Okay, HP is the height of the clay layer after the complete primary settlement, and E sub P is the the void ratio of after the completion of primary settlement. Okay, so solve for E sub P or the new void ratio at the end of the primary consolidation. So in order for us to find the new void ratio, so it's just simply, according to the discussion last meeting, that is simply the original or the in situ void ratio before the primary consolidation minus delta E, that is your E sub P. So how to get the delta E? This one, how to get for the delta, how to find the delta E? So remember the graph of the E log sigma plot. Okay, so according to the formula, our compression index is just simply delta Y over delta X, or that is the slope of our normally consolidated soil. Okay, or as of a primary or under a primary consolidation, sorry. Okay, so that is C sub C, that is delta E over log of this this value. Okay, so rearranging, we have delta E is equals to CC logarithm of this value. So just plugging all the data, we have compression index of 0.28, the overburden or the effective stress of 130, the induced pressure at the top or at the ground surface, that is 50. So delta E is 0.04. So therefore, our E sub P is 0.8 minus 0.04. So that is 0.76. Okay. So now, what is H sub P? This one. What is the thickness of the clay layer after the primary consolidation settlement? So it's just simply the height of the clay layer or the thickness of the clay layer minus your S sub P. Okay, so since our soil is normally consolidated, we have this formula. Okay, so just simply plug in all the values. So plug and chug. So for the primary settlement, we have 0.28 multiplied by 3,000 in millimeters over 1 plus the in situ void ratio multiplied by the logarithm of the delta sigma prime plus delta sigma O over delta over the sigma prime sub O. Okay. So plugging all the values, we have the primary consolidation settlement of 67 millimeters. So after consolidating 67 millimeters after the primary consolidation, so the new thickness of the clay layer is now B 3,000 minus 67 millimeters, or 3 meters minus 67 millimeters. So that is just simply 2,933 millimeters. So this will be your H sub P after the completion of the primary settlement. So this will be your new thickness of the clay layer after completion of primary consolidation settlement, that is 2,933 millimeters. So applying the secondary consolidation settlement formula, or the S sub S, so we can now solve for the secondary consolidation settlement. Okay, so for the formula, C sub S is S sub S is equals to 0.02 multiplied by 2933 millimeters over 1 plus in situ, the E sub P or the new void ratio after the primary consolidation multiplied by the logarithm of your what time do you want to find the answer, that is 5 years over the time it takes for one complete primary consolidation, that is 1.5. So therefore, our secondary consolidation settlement or the secondary compression settlement, that is S sub S, that is 17 millimeters. Okay, so therefore, from 3,000 after primary consolidation, naging 2,933 millimeters. Then after some time, after 5 years, okay, so that is now 17 millimeters secondary consolidation settlement. So therefore, the total consolidation settlement is just simply add all the primary consolidation settlement and the secondary consolidation settlement. So 67 plus 17, you have 84 millimeters na total consolidation settlement. Okay? So that is your solution for problem 3. Okay. So next problem tayo. So example 4, that time required for a 50% consolidation of a 25 millimeter thick clay layer drain at the bottom and top layer in the laboratory is 3 minutes and 15 seconds. Okay, so you have a laboratory work. So drain at both top and bottom. Okay, tama. So drain at both top and bottom. So that is uh, your setup in the laboratory. You have a 25 millimeter stick. So determine the coefficient of consolidation, C sub B of the soil. Next problem is how long in days will it takes for a 2-meter thick clay layer of the same clay in the field under the same pressure increment to reach the same 50% consolidation. So in the field, sand layers are present at the top and bottom of the clay layer. And lastly, how long will it takes in the field for a 30% primary consolidation to occur? Okay, so just to study the problem or analyze the problem. So in the laboratory, you have a 25 millimeter thick clay layer drain at the top and bottom. So during the laboratory works, you find out that that is 50% consolidation under 3 minutes and 15 seconds only. So probably the problem is this one. Okay, so rewriting all the data or the given data from the problem. So your degree of saturation, degree of consolidation is 50%. Okay, your HDR or height of drainage. So since the problem, okay, according to the problem, you have drained both the top and the bottom of the of your sample. So therefore, your HDR will be H over 2 since that is drained from top and bottom. So that is 25 over 2 millimeters. Okay. Then the time it takes for 50% degree of consolidation, that is 3 minutes and 15 seconds. So in seconds, that is simply 195 seconds. So for the solution in problem A, so according to the problem, you just need to find the coefficient of consolidation. So according to the formula, given the time factor T sub V, the time it takes for given degree of consolidation and the height of drainage squared. So that is your formula. So if you study the data, given, we have HDR that is check. We have the time it takes for a specific degree of consolidation, T, that is check. And what we have left is T sub V and RC sub V. Okay, if you recall during the discussion, T sub V or the time factor is just simply depends on the degree of consolidation. Okay, so that is depends on the degree of consolidation. So you have two equation. So for you under 60% and for you that is greater than 60%, or you can also use the table. Okay, so if you check our discussion last meeting, so this is our table. So for a 50% degree of consolidation, so you have a T sub V value or the time factor value of 0.197. So this one. So therefore, so if you now have the value of T sub V, so you can now solve for the C sub V or the coefficient of consolidation. So just plugging all the values. So T sub V, that is 0.197. The time it takes for 50% consolidation, that is 3 minutes and 15 seconds or 195 seconds divided by the HDR squared or the thickness of the drainage. So since both are drained from top and bottom, so that is H over 2. So therefore your H is 12.5 millimeter, 12.5 square millimeter. Okay, then solving for C sub V, that is 0.157853 millimeter squared. Millimeter per second. Okay, so that is your solution for problem A. That is 0.157853 millimeter per second. Okay, next problem, if a 2000 millimeter thick of clay with the same degree of consolidation, so same degree of consolidation or same 50% for problem B, so just simply use again the formula. So T sub V under 50% degree of consolidation multiplied by C sub V times the time it takes for 50% of consolidation, T sub 50%, and the height of drainage to squared. So now you are comparing the laboratory works to actual site condition. So you're considering 2 meters thick or 2,000 millimeter thick of clay with the same degree of consolidation, assuming so the same factor T sub B, since T sub B or the time factor just simply depends on the degree of consolidation. So since they are both 50%, so that is the same value of 0.197. So for the HDR or the height of drainage, so again, we are considering drainage at both sides. So that is 2000 over 2. So since they have the same soil, so therefore, C sub V is also the same. So that is 0.157853 millimeter per second. So since my C sub V value is millimeters per second, and my HDR or the height of drainage in millimeters, so both the unit of millimeter will be canceled out, then what you have left is 1 over seconds. So that is the time is in seconds. Okay, so plugging all the values, so you get the time it takes for 50% degree of consolidation. So that is 1.248 million seconds. So convert it to days. So divide to 60 in minutes, divide to 60 in hours, and divide by 24 for days. So the time it takes for the same degree of consolidation with 2 meter thick clay is 14.4 days. So imagine for 25 millimeters, it took only 159 seconds. Okay. However, for 50%, the same degree of consolidation, that is 50%, and the 2-meter thick layer, you took 14.44 days for a complete 50% settlement. Okay, next problem is how long again in days it will take in the field for a 30% primary consolidation to occur. Okay, so take note that in the laboratory you found out that that is 50%, and in actual site condition you want to check if what is the primary consolidation 30%. Okay, so just simply use the sorry. Again, for solving for that equation or that problem to find the time it takes for 30% consolidation. Okay, so using this formula, so the time factor is now changed to 30% degree of consolidation. So from our table, okay, variation of time factor with degree of consolidation. So for degree of consolidation of 30%, the new time factor is 0.0707. So using that factor T sub V, so plugging all the values, we have the same height of drainage of drain at both sides, that is 2000 over 2. The time it takes for 30% consolidation and coefficient of consolidation. So take note that it is the same soil obtained from the laboratory in the previous problem. So that is the same value of CV, that is 0.157853 millimeter per second. Okay, so plugging all the values, we now have this equation. Then solving for the time it takes for 30% degree of consolidation, we have 447,886.2944 seconds. So converting that into days, we have 5.2 days. Okay, so just take note that if you have new degree of consolidation, so you have a new variation of time factor and the degree of consolidation. So you have a new with time factor T sub V. So you have different consolidation, different time factor. So if you take notice that in problem B, you have 50% consolidation, it took 14.4 days. So however, for 30% primary consolidation, it only took 5.2 days. So therefore, we can conclude that syempre, mas konti or the lesser the degree of consolidation, the lesser the time it took for that degree of consolidation settlement. Okay, so it is directly proportional. So moreover, taking other solution, so only applicable if our degree of consolidation are both U that is less than 60%. So this derivation is only for degree of consolidation that is 60%. So if you take notice that in the previous lecture, the formula, okay, the formula for the formula for T sub V is pi over 4 U squared. Okay, so that is the time factor for U that is less than 60% degree of consolidation. So all other values are constant, all other values in constant, and what you have left is varying variable U. Okay, so that is why in this equation, this equation is only applicable or only fits for the same time factor that is less than 60%. Okay, this one. Okay, using this derivation, using this factor formula expression, so the time it takes for 50% degree of consolidation, taken from the lab to the field. Okay, taken from the lab to the laboratory to the field. So by problem B, okay, for B, so the time it takes for 50% is just simply CV times the time it takes in the laboratory over the height of drainage in laboratory setup, is also equals to the formula C sub V times the time it takes for the field at that specific degree of consolidation over the height of drainage in the field squared. Okay, so T sub 50 is the same, C sub V is the same, so you can cancel out C sub V uh, and this one. So that is what you have left is this expression. T lab over HDR squared in laboratory, that is also equals to the time in field over the squared of the height of drainage in the field. So therefore, okay, so I think we can erase this one. So therefore, given that expression, just plug in the data from the laboratory. So that is 195 seconds over the height of drainage in laboratory. That is also equal to the time in field over the height of drainage in field. You also get 14.44 days. Yan. However, for the different degree of consolidation, so you can also use this notation. So the time it takes for the specific degree of consolidation is also given by the same equation, T sub V, C sub V over times T over HDR squared. So that is with relationship to U squared. So from the formula earlier that the value of TV is pi over 4 U squared. So that value of TV is related to U squared. Okay, so therefore, that time is also directly proportional to U squared. Okay, this time is also directly proportional to U squared. So therefore, we can say that T1 over T2 is also equal to U sub 1 squared over U sub 2 squared. Okay, so what is T1? T1 is the time it takes for a degree of consolidation U1. Okay, and T2 is the time it takes for a degree of consolidation U2. Okay, so going back 14.4 days, it takes for a 50% degree of consolidation. So how long does it take for the same setup, which is in the field? So T2, the time it takes for T2 in 30% degree of consolidation. Therefore, you have 5.2 days. Okay, this one. So take note again that this solution only applicable if you are both 60% or you that is less than 60%. Okay. Last problem. Okay, for the last problem, example problem, the calculation of consolidation settlement under foundation. So this reference is come from this problem is come from the book of Principles of Geotechnical Engineering 8th edition by Das, Braha and Das. Okay, so calculate the settlement of a 3-meter thick clay layer given in the figure that will result from a load carried by a 1.5 square meter footing. Okay, so the clay layer is normally consolidated. Okay, use the weighted average method to calculate the average increase of effective pressure in the clay layer. Okay, so given the soil profile and this setup, so we have a footing size of 1.5 by 1.5 meter. Okay, we have 890 kilonewton applied on the footing. Okay, the footing embedment is 1.5 meters. Okay, the dry unit weight of sand is 15.72 kilonewton per square meter. So we have a 3-meter thick dry sand. And also we have 3 meter thick of saturated sand. So we have a groundwater table right here. So that is 3 meter thick of saturated sand. So that is that have a unit weight of 18.87 kilonewton per cubic meter. And again, we have a clay layer of a 3 meter thick clay layer with a saturated unit weight of 17.3, an in situ void ratio of 1.0, and the liquid limit of 40. Okay, so using the weighted average method, so if you recall your geotechnical engineering, if you tackle this problem, settlement of under foundation, or the Bosnian-Q equation, so to get the stress at that specific point, so if you tackle that into your geotechnical engineering, so you can use the concept of Bosnian-Q or Bosnian equation, okay, so Bosnian equation, in order for us to find the stress at a specific depth. Okay, so what is the stress at that specific depth? So using the weighted average method, so let's recall that method to calculate the average in pressure stress. Okay, so for normally consolidated clay, again, we have this formula. So S sub P, or the settlement, primary consolidation settlement, C sub C times H over 1 plus E sub 0, logarithm of effective stress plus the induced pressure over the effective stress. However, in consolidation under a foundation, okay, under the foundation, that induced pressure will be from the Simpson's equation, delta Q average. Okay, so again, that induced pressure is not what you have on top, what you have the value, what is the pressure on top. So under set up for elastic foundation, so that value will now change, for that induced pressure will now change. So how to use delta Q average, delta sigma average. So for delta sigma average, you will be using the Simpson's equation to approximate the delta sigma average, or the this value. Okay, so just is simply the delta sigma prime at top plus 4 times delta sigma prime at middle plus delta sigma prime at bottom divided by 6. So that is your Simpson's equation for delta sigma average. Okay. Notation, delta sigma M, delta sigma T, and delta sigma B are below the center of the footing and can be obtained from the 2:1 method. So we'll be using the 2:1 method. So 2:1 meaning the stress line, okay, this one. So this will be our foundation. Sorry. So this will be our foundation. Again, so this one. So 2:1 meaning your stress line is have a ratio of 2 vertical, 1 horizontal. 2 vertical, 1 horizontal. So also have this ratio of 2 vertical, 1 horizontal. So that is your 2:1 method. Okay. So before we go for the delta sigma average, so we need to find all the data that we have learned. So how to solve for the data that we have learned during the discussion. So C sub C. So again, we are assuming that we have undisturbed clay. So we are using the Skempton's formula. So 0.009 LL minus 10. Okay, so 0.009, 40 minus 10, we have 0.27. Okay, again, H is equals to 3,000 millimeter, E sub 0 is equals to 1.0. Okay, so the in situ void ratio is 1.0. So since we have this set up, okay, how to solve for the effective stress. So just simply take the effective stress at the middle of the clay layer. So at this, okay, so at this location, this one. So at the middle of the clay layer. So it's just simply equal to 3 times the, okay, 3 times the dry unit weight of sand, okay, plus 3 times the saturated unit weight of sand minus gamma water, or the unit weight of water, plus 3 halves, or the mid portion of the clay layer. So that is 1.5 multiplied by the saturated unit weight of clay minus unit weight of water. Okay, so again, effective stress is equals to 3 times 15.72 plus 3 times 18.87 minus 9.81 plus 1.5 times 17.3 minus 9.81. So you have your effective stress of 85.58 kilonewton per square meter. Okay. So going back to the equation, this one. Yeah. So from the Simpson's equation, we have the delta Q average from the Simpson's equation, this one. So we need to find the delta sigma prime at top, delta sigma prime at middle, and delta sigma prime at bottom of the clay layer using the 2:1 method. Okay, so this one. So this one is you need to draw an elastic line from the top of from the bottom of the footing to the bottom of the clay layer. Okay, so this ratio, okay, this ratio over here is 2:1. Therefore, you have a ratio of 2 vertical. Again, sorry, that is happening. Okay. Okay. This is 2 vertical, 1 horizontal. Okay, so we need to establish the lengths or the depth at each location. So from the top of the clay layer, that is 4.5 meters from the bottom of the footing. So from the middle of the clay layer, that is 6 meters from the bottom of the footing, and the bottom part of the clay layer, that is 7.5 meters from the bottom of the footing. Okay, so what is delta Q prime? Okay, so delta Q prime is just simply what is the stress at top, what is the stress at the bottom, and what is the stress at the middle. Okay, delta Q prime is denoted as this equation, this one. So how to derive this equation? So saan ba nanggaling tong equation na to? So again, if you recall, stress is just simply force over area. So we know the force load, that is the Q at top. This is the load at top. Okay, this is the load at top. And this one should be the area. Okay, so what area is B plus Z and L plus C denoting? Okay, this one, okay, that area is just simply what is the area at this location, at this top clay layer. Okay, what is the area of the projection of this 2:1 stress line? So what is the projection of this area at this top layer? At the middle layer, what is the area? And at the bottom layer, what is the area? So if you check this elastic line or stress line. So for example, we have this curve line, this one, this one, so this one, yeah. So imagine this is the bottom of the footing. Okay, this is the bottom of the footing with length B. Okay, so this is Z. Okay, this one is Z. Okay, Z is the elevation from the bottom of the footing. So from the ratio of 2:1, so this is 2:1. So this should be Z. So this is Z over 2, and this is Z over 2. So this is your length Z over 2. This is your length Z over 2. And this is your length B. So how to solve for the length of the total length of this projection line? So it's just simply B plus Z over 2 plus Z over 2. Okay, Z over eraser. So that is Z over 2. So 1/2 of Z plus 1/2 of Z, that is 1Z or Z. So that is why we have this notation over here. Okay, so doing that on the side of L, okay, on the other side, doing that on other side. So let's say this one is L. Okay, this one is L. Same projection, 2:1. L, this is L. So you just need to erase B and change it to variable L or L length. So this is exactly what you have over here. Okay, so that is the derivation of that formula. So it's just simply the area of the projection of 2:1 ratio. Okay. Okay. So that is the projection of the area. So doing that in our problem. So at top, okay. So delta sigma prime T. So your load on at top is 890 over 1.5, which is your B. Then the projection from the bottom to the top of the middle clay layer, that is 4.5. And again, your L is 1.5. And the projection is 4.5. Therefore, you have sigma prime T or delta sigma prime T, you have 24.72 kPa. Then at the middle of the clay layer, that is 6 meters below the bottom of the footing. So delta sigma prime M, so the load at top is 890 over B plus Z, but that is 1.5. Your Z is 6 meters multiplied by 1.5 plus 6 meters. Again, you have 15.82 kilonewton per square meter. Then for the bottom of the clay layer, so that is the symbol delta sigma prime B. So the Q load on top is 890 kilonewton over B plus Z, L plus Z, which your Z is 7.5 meters and your B is 1.5 meters. Your delta sigma prime B is 10.99 kPa or kilonewton per square meter. So therefore, using the Simpson's approximation, delta sigma average is 24.72 plus 4 times 15.82 plus 10.99 divided by 6. Therefore, your delta sigma average is 16.5 kilonewton per square meter. So this value, so this delta sigma average, so I need to put delta. Okay, this one, this is delta, and this one should be delta. Okay, so this value of 16.5 kilonewton per square meter will now be used in this equation. So just simply use that Simpson's derivation or Simpson's approximation for this value. So therefore, the same setup. So plug in the value of compression index, the value of your thickness of the clay layer, your in situ void ratio, your effective stress at the middle of the clay layer, and the average or the delta sigma prime average using the Simpson's approximation. Therefore, our SP or the primary consolidation settlement under a foundation, elastic foundation, is 31.01 millimeters. So that is your solution to problems relating to the consolidation settlement under elastic isolated footing. Okay, so for your homework, this have a duration of 1 week. Okay, so you have this homework, you have your answer 511 days. Okay, so this problem is very challenging. So take note that you have a laboratory setup and field setup. Okay, so that is 511 days. Then again, this one is time consolidation problem also. So how long it takes for the clay layer to reach 50% consolidation, and what is the settlement using that 50% consolidation. So you need to use this equation of coefficient of compressibility. So please take note of this equation. So this equation over here is the corrected formula for the coefficient of compressibility. So I checked the our module 1, your A sub V is delta E plus delta P. So it should be the delta E over delta P, or the change in void ratio over the change in pressure. So please take note of this correction. And last, for your homework 1, estimate the primary consolidation in the clay layer given by this soil profile, which H1 is equals to 2 meters, H2 is 4 meters, and H3 is 6 meters. Okay, given the soil properties of sand and the soil properties of clay. So use again the assumption of Skempton's equation of undisturbed soil. Okay, so that is how to get your compression index. Okay, then for the answer, that is 13.8 centimeters or approximately 138 millimeters. Okay, so for the reference of our discussion today, we have Das and Sivakugan, Fundamentals of Geotechnical Engineering, the Holtz, Shannon, and Kovas Introduction to Geotechnical Engineering, and the Principles of Geotechnical Engineering by Das, and the Wikipedia Soil Consolidation. Okay, so again, do you have any questions? Okay, so thank you for listening.